Hi, this is Michael Pfeifer. Welcome to another episode of the Metal Conversations podcast. In this episode, I'll discuss metal fatigue. This is a companion to several articles that are on our website. Metals degrade when exposed to stressors. Stressors are external forces or chemicals and different things that act on metals that can cause metal degradation. This includes mechanical loads, heat, rubbing metals against each other or against other materials, exposure to chemicals, water, electricity, radiation, bodily fluids, and other things that can cause metals to degrade. What we don't want to have happen when metals are exposed to stressors is for metals to degrade to the point where they stop performing as needed and they fail. So the thing I'm going to talk about today is metals' response to cyclic stresses, that is, repeated stresses that can cause cracks to form and grow inside of the metal and result in fracturing of the metal and failure of the component. Some examples of components that are exposed to cyclic stresses are aircraft wings and the fuselage, the landing gear for airplanes, for automotive crankshafts and drive shafts, and the suspension springs. There are two situations where this is a problem. One is during product testing, when people are testing their product, and the other case is when components fail during product use and then the product stops working. The problem with failures during testing is that then the design team has to figure out the root cause of the failure, implement a fix, and then retest the product. If the retest is not planned for, then this results in delays of releasing the product and starting to sell the product. Testing typically takes several weeks to perform. Failures during use still have to figure out the root cause and then implement a fix. With fatigue, cracks form and grow due to a cyclic stress acting on the metal component. Cyclic stress means that the stress on the metal is cycling between a high stress and a low stress. And what happens is that the nominal stress on the component, that is the stress over the entire component's cross-section, is less than the metal's yield strength, but the stress at a localized point is greater than the metal's yield strength. And just as a reminder, the yield strength is the stress at which a metal starts to deform. There are things that can result in stresses at a local point on a component being higher than the metal's yield strength, and that can result in cracks forming and then growing at that location. Sources of cyclic stresses include the applied loads, bending because the stresses on a component aren't aligned, vibration, acceleration and deceleration of the component, and thermal expansion and contraction. These are some examples of sources of cyclic stresses. There are others. And again, what happens is that the local stress is greater than the nominal stress, and this occurs because of stress concentrations on a component. Stress concentrations are locations where the stress at a local point is greater than the nominal stress over the entire cross-section of the component. Examples of stress concentrators are notches, weld joints, surface roughness. Even on a smooth surface, intrusions and extrusions can form at the smooth surface, and those act as stress concentrations. So at a stress concentration, the stress is higher than the nominal stress, and the stress can exceed the metal's yield strength, and as a result, a crack forms in the component. When the stress at a local point is greater than the metal's yield strength, and there's cyclic stresses, then microcracks form after some number of cycles. The number of cycles to crack formation depends on the metal's strength. The higher the strength of the metal, the longer it takes for cracks to form. It also depends on the magnitude of the stress. The higher the stress, the fewer the number of cycles before cracks starting to form. Also, the presence of stress concentrations and metallurgical factors influence the number of cycles it takes to start forming cracks due to cyclic stresses. With continued cycling, the microcracks coalesce into larger cracks, and then the larger crack grows with continued cycling. As the crack grows, the cross-section of material that's intact, that's supporting the entire load on the component, is decreasing. And what that means is that the stress on the intact material is increasing. So as the crack grows larger and larger, the cross-section area of intact material decreases and the stress increases, and it reaches a point where the remaining intact material can't support the applied load and the component fractures completely. There are a few requirements for fatigue to occur. There has to be a cyclic stress on the material. The stress has to be, at least a component of the stress has to be tensile in nature. So there has to be a tensile stress, and we have to have the localized stress that exceeds the metal's yield strength. There are a number of things that we can do to prevent fatigue based on understanding the requirements for fatigue. First of all, we can do things to minimize cyclic stresses on a material, especially if they're coming from other sources other than the applied load. So it's important to know the stresses on components. We also can design components so that they don't have stress concentrations, or reduce the stress concentrations so that it reduces the increase in the stress at a localized area. We can make components using processes that result in lower surface roughness, which results in less stress concentrations and improved fatigue resistance. Certain manufacturing processes result in a rougher surface compared to others, and choosing the process that results in lower roughness will help improve fatigue resistance. From the metallurgical perspective, we can do things with the metal to improve fatigue resistance. We can improve its strength through heat treating, through case hardening. Inclusions and manufacturing defects inside of the metal act as stress concentrators, and these inclusions are non-metallic inclusions. Non-metallic inclusions are a result of the metal making process, so they arise during steel making or aluminum making or stainless steel making. These are small, hard particles that act as stress concentrations, and special processes can be used to minimize the number of inclusions in the material that will help improve the fatigue resistance of the material. Such materials do exist. They are more expensive, but they're used in situations where fatigue resistance is very important, for example, in aerospace applications. Also, minimizing manufacturing defects such as laps and seams and voids. So using suppliers that have good control over their manufacturing processes is important to minimize manufacturing defects that can act as stress concentrations that can reduce the fatigue life of components. So those are some of the things we can do to improve fatigue resistance and prevent fatigue from occurring. What we can also do to understand the fatigue resistance of the alloys we're using and of the components we're designing is to do materials level testing prior to product testing. So we can assess materials and component designs prior to testing to understand the fatigue resistance of the materials and of the component designs, and to generate data that will help with the selection of the materials and selection of the design, so that when it comes time for product testing, there's a high confidence that the materials and the design that's selected will work in the final application. It takes more time and more money to do the materials level testing, but it saves a lot of time and money associated with having to deal with failures during testing and having to repeat testing. If you'd like to learn more about fatigue, see the articles on our website. The links to the articles will be included in the notes along with this podcast, and we also list other resources. Finally, we help with design to help prevent fatigue, and also in failure analysis when there is a failure due to fatigue. And the link to our website is included if you need help with that. You just reach out and we would be happy to meet with you to discuss your design or the failure, to see how we can help out and discuss the next steps. So that's it. Thanks for listening, and good luck with your metals. Bye.